Hi students, so let us continue the frequency response of a system. So now in the previous case we have considered two cases where if we have a finite pole, how does the frequency response looks like? If there is a finite zero, how does the frequency response of that system will look like? So now let us consider the open loop transfer function, which is GFS into HFS, having negative feedback. If it has got a pole at the origin, how does the frequency response of this look like? So as we know that we are replacing S by j omega, then this equation g of j omega h of j omega will become 1 over j omega. So we are supposed to know the magnitude of this g of j omega and h of j omega. These are the magnitude, which is nothing but 1 over square root of course there is no real part, it is actually 0 square plus omega square. So this happens to be 1 over omega. This is 1 over omega. If you want to find the magnitude of this g of j omega h of j omega in dBs, I need to make 20 log of to the base 10 1 over omega. So then this can be written as minus 20 log omega. I will not write the base as 10. It is understood that the base is 10. So this is what is minus 20 log omega is the magnitude of this. So how about the phase? So phase angle of g of j omega and h of j omega is nothing but of course tan inverse of this is actually 0 plus j omega. So what you have is it's like the imaginary quotient is omega, the real value is 0. So it is tan inverse of, suppose if you have a plus jb as the parameter, its phase angle is actually tan inverse of b by a. So what you have now is, of course, if it is 1 over this, then this becomes minus tan inverse of. So that's the only difference. Now you have it as 0 plus j omega, then it should be minus tan inverse of. So this is minus tan inverse of, the imaginary coefficient is omega, the real coefficient is 0. So actually here g of j omega into h of j omega phase angle is minus tan inverse of omega by 0. So this is actually minus tan inverse of infinity. We know that tan inverse of infinity is 90 degree. So this is minus 90 degree. So the phase contributed by a term, a pole at the origin, is always minus 90 degree. So it will not change with the frequency. So it is independent of omega, the phase contribution is always minus 90 degree. Whereas the magnitude is going to change because magnitude is given by minus 20 log omega. Suppose what we'll do is, so let us take the value of omega and the magnitude. So magnitude is actually minus 20 log omega. So this is my magnitude. So let us try to find out values of the magnitude for different values of omega. So let us take some values. So now let me take it as 0.1 and 1. It is 10, 100. Let us find the magnitude of minus 20 log omega for these values of omega. So what I'll do is minus 20 log of alpha a. So this I'll calculate what is this 20 log of a for different values of a. Let a be 0.1. You can see now it is, this is actually in dBs. So this is 20 dB. Next calculate for omega of 1. So it is now 0. Then calculate for omega of 10. You can see now it is minus 20. Calculate for a value of omega which is 100. You can see now minus 40. So this is minus 40 dB. So these are all the magnitudes of this term as the value of omega changes from, this is actually in radian per second. So this is the different values of frequency and this is the corresponding magnitude. So now what I'll do is, let let me try to write that. So this is your omega. So let me write the omega values as this is 0.1. Let this be 1. So let this be 10. Let this be 100. So let the magnitudes be 0 dB here. Let this be 20 dB. Let this be 40 dB. So let this be minus 20 dB. So let this be minus 40 dB. Now let us mark against the frequency what is the magnitude. You note the frequency is 0.1 here. So this is 0.1. The corresponding magnitude is 20 dB. So let me point out this is point A. So if I say this as point A, B, C, D. So this is A, B, C, D. So this is A. For omega is equal to 1, the magnitude is this. So this is B here. And for a frequency of 10, the magnitude is minus 20. So this is actually point C. And for this 100, the magnitude is actually minus 40. So now this is the thing. So if I join all the points, it happens to be this. See now, so this is a straight line. This is a straight line with its magnitude as 0 dB at 1 radian per second. See here. So when the frequency is 1 radian per second, the magnitude is 0 dB, and this will have a slope of 20 dB per decade, meaning when the frequency changes by 10 times, the magnitude reduces by 20 dB. See here, is your frequency increased by 10 times? So this is 1 decade. How much is the change in magnitude? Has it gone down? Minus 20 dB. So I can write the corresponding magnitude of this 1 over S would be a straight line with a slope of minus 20 dB per decade passing through 0 dB line at omega is equal to 1 radian per second. 1 radian per second. So this is what is the description or the magnitude of the term which is corresponding to a pole at the origin. Now let us consider a 0 at the origin. Suppose if you consider a 0 at the origin, of course we know that 0 at the origin looks like this. This is GFS into HFS. It is equal to S. Now this is representation of a 0 at the origin. So if I want to know the magnitude of this, replace S by J omega, then magnitude is G of J omega into H of J omega is equal to J omega. Sorry, the magnitude. Of course, magnitude of this is, when I say the magnitude of this actually becomes, so 0 square plus omega square, of course under root of, then this will become omega. If you want to find the magnitude in dBs, which is G of S into H of S, magnitude in dBs is actually 20 log of omega. Again, if you want to find the phase of it, so as we know that in the previous case also, it was actually tan inverse of B by A. So in case of B you have it as omega, in case of real part it is 0, it's actually 90 degree. So this is plus 90 degree. So the phase of GHS is equal to plus 90 degree for a term which is for a pole at the origin. We saw in the previous case, if you have a 0, this is, let me just clarify, this is a 0 at the origin. If you have a pole at the origin, then the phase is minus 90 degree. So since it is a 0 at the origin, the phase is plus 90 degree. Let us see how does the magnitude goes. Again, let us give different values of omega and the magnitude, which is 20 log of omega. Give it as 0.1, 1, 10, 100. Maybe you can just give the value. If you give it as 20 log of, it is now, I think you have the same value, but instead of minus, let me just take out that minus. It's 20 log of alpha A. So next, calculate for 0.1. You can see now it is minus 20. This is minus 20. For here it is 0 dB. If you just do it for 10, it's actually plus 20 dB. For 100 it will be 40 dB. So these are all in dBs. If you actually write the line corresponding to this, or the magnitude asymptotic thing, so this is omega starting from 0.1, 1, 10, 100. Suppose if you write it so. So magnitude at 0.1 radian per second is minus 20. At 1 it is 0. At 10 it is plus 20. At 100 it is plus 40. So it will be line with a slope of plus 20 dB per decade, with its magnitude crossing 0 dB. This line is crossing 0 dB when omega is equal to 1 radian per second. 1 radian per second. So now if we summarize, suppose if we have a pole at 1 plus 0.1 s. So how does the magnitude plot of this look like? So as we know from the earlier case, earlier understanding, this cutoff frequency is, so it's actually tau. So this is tau. So frequency happens to be 1 over tau, which is 10 now. So till 10 radian per second, till 10 radian per second, this will have a magnitude of 0 dB. This till 10 radian per second will have a magnitude of 0 dB. Afterwards, it decays with a slope of minus 20 dB per decade. Similarly, if you have a term which is 1 over, maybe 1 plus 0.2s. Now there is a 0 at a finite place. Now where is 0? So tau z is nothing but 0.2. Then what is omega z? It is actually 1 over tau z. So 1 over 0.2 is 5. 1 over 0.2 is 5 radian per second. So the meaning of this now is, so from maybe assume that it is 0.1 radian per second, assume that this is 5. This is 5 radian per second. So if you are having a term which is a finite 0 at 5 radian per second, which is corresponding to a tau of 0.2. So what does this mean is, so till 5 radian per second, this will have a magnitude of 0 dB. After 5, the magnitude increases at a slope of plus 20 dB per decade. Plus 20 per decade. Fine. And of course, if you have a pole at the origin, we have seen that. So it's a straight line passing through 0 dB line with a slope of minus 20 dB per decade. This is the slope. The slope is minus 20 per decade. And we saw when there is a 0 at the origin, now it will have a slope of plus 20 per decade, again passing through 0 dB line at 1 radian per second. And of course, we have seen the magnitude plots also for a finite pole, a finite 0, a 0 at the origin, and a 0 at the a pole at the origin. So now let us take some specific example and try to plot the frequency response. So maybe you might have seen so far frequency response, which consists of magnitude response as well as the phase response. So in control systems, this was discovered by an engineer called Bode. So that's why these plots are named after him as Bode plots. So this Bode plots consists of two plots. One is magnitude plot, and other one is phase plot. So how does the magnitude changes with respect to frequency? How does the phase changes with respect to frequency? Now let us consider a system which is unity feedback, and that too it is a negative feedback system. Let us assume that its GFS into HFS is in the time constant form, and it is, assume that it is 10 divided by 1 plus 0.1 s and 1 plus 0.01 s. Assume that these two are the poles. These two are the poles at minus 10 and minus 100. Suppose if I write the pole 0 plot of this, how does this look like? Will it not look like this? So there is a pole at minus 10, so there is a pole at minus 100. So this is a second order system having poles at finite points, so on so. Now actually this has got three magnitudes. So one of the magnitude is 10, other magnitude is 1 over 1 plus, so let me list the terms here. So this is now 10, other term is 1 over 1 plus 0.1 s, the other term is 1 over 1 plus 0.01 s. So these are the individual terms. Suppose if I draw the magnitude of each one of the term individually, assume that this is 0 dB line, or this is just the reference. Now let me write some reference here. Let me write some reference. This is not okay. Some reference here. Don't think this is 0 dB. So this is some reference line. So let us assume that the magnitude is, or the frequency omega is 0.1 radian per second. Let us take this as 1. Let us take this as 10. Let us take this as 100. Let us have the magnitudes keep going up here like this. So let us take these are the magnitudes, sorry, some reference points. Now if I want to know the magnitude of this in dBs, so what is that? So 10 can be represented in dBs as 20 log of 10. 20 log of 10. So what is 20 log of 10? If you actually do 20 log of 10 is actually 20 dB. So this is 20 dB. See now, this is a constant term and there is no omega involved in this. So for values of omega starting from 0.1, 1, 10, 100, the magnitude remains the same as 20 dB per decade. So if I consider this as 0 dB, so if this comes out to be 20 dB, so is it not a constant line? This is the magnitude of 10, which is equal to 20 dB. It is independent of frequency. It's independent of frequency. It is constant value. Now let us consider this is done. We are done with this. So let us consider this term, 1 over 1 plus 0.1 s. So as we saw in the previous case, such a pole at 10 radian per second will have a magnitude of 0 dB up to this cutoff frequency, which is 1 over 0.1 is 10. Afterwards it decays with a slope of minus 20 per decade. Now let me just do the same thing here. Since you are writing it for this, I know that this will have a magnitude of 0 dB till where? Till 10 radian per second. Shall I write it here? This is 0 dB line, and then after you can see this is up to 10 radian per second, it is 0 dB. Afterwards it decays with a slope of 20 dB per decade. So how do you find 20 dB per decade? So what you can do is come down by 20 dB. You are coming down by 20 dB. Go by 1 decade. When I say 1 decade, whatever is the frequency here multiplied by 10. Since it is 10 here, 10 into 10 is 100. This is here. So this is my point. And now join this and this. Join this and this. Is this not 20 dB per decade? So now this has a slope of minus 20 dB per decade. Let me again repeat. Wherever the cutoff frequency comes, for this the cutoff frequency is 10 radian per second, which is 1 over tau. So from this point come down by 20 dB. So you come down by 20 dB, go by 1 decade. When I say 1 decade, make the frequency 10 times. Since you are there at 10, you go to 100. So you go to 100. Mark this point and join the line, join this dot to this dot, let the line passing through those two dots. So this is a line of minus 20 dB per decade. So we are done with this also, we are done with this also. Next we need to plot for this. So what does this says? Now it is similar to this. It is a 0 dB line till where? Till 1 over 0.01. 1 over 0.01 is actually 100 now. So till 100 radian per second, this will have a magnitude of 0 dB. See now, this is 0 dB line till where? Till 100 radian per second. After 100 radian per second, it goes with a slope of minus 20 dB per decade. Then how do you find 20 dB per decade now? So as we did it here, again from this point you come down by 20 dB. So this is my 20 dB point which is coming down from here. Go by 1 decade. So what is 1 decade of 100? So 100 into 10 is, so 100 into 10 is actually 1000. So you identify 1000 here. So this is a point. You came down by 20 dB, go by 1 decade. Now join this and this line. This and this line. So what is the slope of this? This is again minus 20 dB per decade. Fine. So this is my plot of individual terms, which is 10.1 over 1 plus 0.01s and 1 over 1 plus 0.01s. So these are individual, but what I want is the overall plot of this transfer function which has got all the three terms. So to do that, you have to simply add all the three. So this is there plus this plus this. If you add all the things, you'll get the the frequency, sorry, the magnitude plot of this particular transfer function. So for that, let me write it here. So let us take this as my reference line. This is a reference line. So what is the magnitude at 0.1 radian per second? So you can see this is contributing 0, this is contributing 0, whereas this is contributing 20 dB. So the addition of this plus this is actually 20 dB, correct? If you consider this as 20 dB, so this is 20 dB. So is this magnitude of 0 dB, 0 dB, 20 dB continues till this point of 10 radian per second, till the first cutoff frequency? So see here, between this and this, so between this and this, what is this? This is 20, this is 0, this is 0. So what is the addition of this? So we saw the addition of that at the beginning is 0, 0 plus 20. So is that 0, 0 plus 20, 0, 0 plus 20, will it continue till where? Will it not continue till 10 radian per second? Because my first cutoff frequency starts at 10 radian per second. So till the first cutoff frequency, the magnitude goes as 20 dB per decade till the first cutoff frequency, correct? So this is my resultant plot. It is the addition of all of them for this particular transfer function. This is done now. Next what happens? This is 10 radian per second. So this is 0.1. Then what happens? See here. How much is the slope now? Just identify the slope. Is the slope of this is 0? Meaning it's a horizontal line. Is the slope of this is minus 20 dB per decade? That is this line. Is the slope of this is still 0? So once your first cutoff frequency comes, don't bother about the magnitude. Look at the slope. Look at the slope. What was the slope here till? Can you see the slope of this is 0 dB per decade, 0 dB per decade, 0 dB per decade. This is also 0 dB per decade. Now let us move from here and let us now see what is the slope. Is the slope 0 here? Is the slope minus 20 per decade? Is the slope 0? Now what is the resultant slope? The resultant slope is the slope of this plus slope of this plus slope of this. Is it not 0 plus of minus 20 plus of 0? So this is minus 20, 0 and this is 0. So now from where to where this will have a slope of so and so? From this point to 100 radian per second. So now I have to draw a line corresponding to minus 20 dB per decade. So for that, come down by 20 dB, go by 1 decade, draw the line. Draw the line till next cutoff frequency. Next cutoff frequency is there at 100, because at 100 you have a different slope. You have a different slope for this. Now you have extended this line only up to 100. Only up to 100. Then after 100, this is actually 100 radian per second with a slope of minus 20 degree. See now, after 100, what's the slope of individual lines? So let me write this also here. Is the slope of the first line 0? Is the slope of the first line 0? Is the slope of second is minus 20? Do you have another minus 20? So sum of the slopes, is it not 0, minus 20, plus of minus 20? Is the slope now minus 40 dB? That is, after 100 radian per second, the slope changes from minus 20 to minus 40 dB per decade. So how do you do now? Come down by 40 dB, go by 1 decade, draw the line. So this is minus 40 dB per decade. Got the point? What we did, we took the individual terms 10, 1 over 1 plus 0.1, 1 over 1 plus 0.01s. We wrote the individual plots. This is for 10, which is 20 log of 10, which is 20 dB. See now, this is plus 20 dB. So this is a 20 dB line. We know that if you have a pole which is at 1 over 1 plus 0.1s, it will be a 0 dB line till the cutoff frequency, which is 1 over tau, that is 10 radian per second. Afterwards, it decays with a slope of minus 20. Then this is again 0 dB line till 1 over tau, that is 100 radian per second. Afterwards, it goes down. Next, once you are done with the individual plots, I need to draw the overall plot. So overall plot is what? It is the addition of all the 3 plots because they are in dBs. Because we know that this you need to divide, but in case of this is what you have, this divided by this divided by this. So now since we are putting them in dBs, you are simply adding all of them. So when you add all of them, so you try to add the magnitudes as well as since the slopes are 0, 0, 0, you can simply add the magnitude. So magnitude of this is 20, this is 0, this is 0. So you start with 20 dB. This will continue where? Till where? This will continue till 10 radian per second. So these are all radian per second. This is omega in radian per second. Then the first cutoff frequency starts at 10 radian per second. The slope is minus 20 by decade. Okay, that's what we saw here. Between 10 and 100, there is only one slope. So that's why it is minus 20. So how to do this? From this point, come down by 20 dB, go by 1 decade. When I say go by 1 decade, you just increase the frequency by 10 times. So you got this point. Then at 100, there is one more change in slope. You can see this is anyhow I have a slope change at 10 radian per second. That will continue here. That will continue till ever. So after 100 radian per second, you have 0 dB slope. This is minus 20 dB slope. This is another minus 20 dB slope. The overall slope is 0 plus minus 20 plus minus 20. So this will become minus 40 dB per decade. So after 100 radian per second, this will have a slope of minus 40 dB per decade. So this is by resultant magnitude plot. Then what is the phase plot of this? So if you want to know the phase of 10, so if you want to write the phase of 10, is it not tan inverse of 0 by 10? This is actually 0 dB. So a constant term will never contribute to phase, This need not be done, but I am saying that a constant terms will not contribute any phase. Now you consider the term which is 1 over 1 plus 0.1. Yes. Is it not contributing minus tan inverse of 0.1 omega? Of course, for different values of omega, you need to find it. And how about for this? This is for the third term 1 over 1 plus 0.01. Yes, which is nothing but minus tan inverse of 0.01 omega. Now, what is the overall phase? Is the phase is equal to forget about this. Is it not minus tan inverse of 0.1 omega minus tan inverse of 0.01 omega? So now you give different values of omega, find out different phase, start from 0 go up to infinity. When you start with 0, it will have a overall phase shift of 0 degree. When you go with omega is equal to infinity, this will contribute minus 90, this will also contribute minus 90. So both are summing up and giving it as minus 180. So give it as 0.1, give it as 1, give it as 10. So for different values of omega, let me just give it. So it is now minus tan inverse of 0.1 alpha A minus tan inverse of 0.01 alpha A. Calculate for 0.1. You can see the phase is minus 0.5 degree. For a phase of a omega of 1, it is a minus 5.7 degree. For a value of 10, it is 45 degree, minus 45 degree. Again, you can just do it for 100. So for 100, it would be minus 84 degree. For 100 omega value, it is minus 84 degree. So likewise, so we can plot for different values of omega what is the phase of the overall system. So this is basically what is conceptually you are trying to understand. How does the magnitude and phase of each of the term will going to constitute the overall magnitude plot and the phases. So once you have the phase, maybe you can write the phase plot also. So let me just approximately draw it here only. If this is phase of 0 degree, this is 0.1, maybe 1, this is 10, this is 100. See now, it goes with a slope of 0 degree. This is 0 degree line, and then at 0.1 it is minus 0.5, almost 0. At 1 it is 5 degree. At 10 it is 45 degree. I'm just approximately writing. At 100 it is minus 84 degree. It goes like this. So it just goes like this. This is a smooth graph. And suppose if it is minus 180 degree line, if it is minus 180 degree line, at values of omega equal to infinity, it just goes to minus 180 degree line. So it just goes from 0 to minus 180. This is how it is going. So this is your phase plot. This is magnitude plot of this particular term, of this particular transformation. Okay. So now we know that you are writing the individual plots and then adding it up and doing all those things. Let us find out. Let us redraw the same transfer function, not by writing the individual plots, but there is some other technique. So let me again take the same transfer function. GFS into HFS is actually 10 by 1 plus 0.1 S and 1 plus 0.01 S. So this is my transfer function. So for this, let us try to understand what is the magnitude at the origin. So I want to know what is magnitude at the origin. So magnitude at the origin, that is what is, when I say origin, it is omega is equal to 0 radian per second, or very small value of omega, maybe 0.1 radian per second or 0.01 radian per second, depending on what is the starting point of your plot. So this is my origin frequency. So which is ideally 0, but typically we cannot start with 0. We'll start with 0.1 radian per second. Now to understand that, we call it as MAO. We know that this will contribute 0 dB, this will contribute 0 dB at the origin. So shall we say that the magnitude at the origin is contributed by only this term? So shall I say it as 20, because usually this will be written as K by 1 plus tau P1S and 1 plus tau P2S, where tau P1, tau P2 are the time constants. shall I say it as 20 log of k is magnitude at the origin for a system without having poles or zeros at the origin. So this is my 20 log of k. So in place of k, what you have? In place of k, you have it as 10. So shall I say now 20 log of 10 is the magnitude at the origin. So when I say origin, it is omega is equal to 0.1 radian per second. This is my this is how I start my plot with the starting value of omega as 0.1 radian per second. Is it not 20 dB? So we found what is magnitude at origin for this plot with the origin frequency as 0.1 radian per second is 20 dB. Next we'll write a table called as slope table. Slope table. In this slope table, we just list all the terms and their individual cutoff frequency and their slope and the overall cutoff frequency. So now our overall slope. So this is my term, this is the cutoff frequency of that particular term, this is the slope, this is the resultant slope, this is individual slope of that term, this is resultant slope. Resultant slope is okay, let me just tell you that. So what is the first term? Okay, you can just leave out this. So first term, okay, leaving out this term because that 10 is considered in the magnitude. So is it not 1 over 1 plus 0.1? Yes. So cutoff frequency is actually 1 over this tau. So it's actually 1 over 0.1, which is 10 radian per second. Since it's a first order finite pole, its individual slope is minus 20 dB per decade. So now prior to this I didn't had any slope. This is also minus 20 dB per decade, meaning this is my slope starting at 10 radian per second. Before this 10 radian per second I didn't had any slope, I didn't had any term which is having some slope, so that's why these two are same. So next term is you write it in the order of increasing cutoff frequency. Is it not 0.01? Yes. Is it not 1 over 0.01, which is equal to 100 radian per second? Now this will have a slope after 100 radian per second, which is equal to minus 20 radian, 20 dB per decade. That is this one. So what we are trying to do is, so this is that term 1 over 1 plus 0.01. So is the cutoff frequency 100? So after 100 was the slope? Is it not minus 20 per decade for this particular term? So it is what is, this is minus 20. So what is this resultant slope? Resultant slope is something like this. It is the addition of slopes at frequencies after 100. See now, after 10 up to 100, did you have the resultant slope as this is not contributing anything? Does this only contributing? This is also not contributing. So what is the resultant? Is minus 20. So after 100, can you see the resultant slope is, this is already there and this is adding up. So what is the resultant slope? It is the addition of this plus this, which is minus 40 dB. So resultant slope is of this is the earlier slope plus the present slope is equal to present slope is minus 40 dB per decade. So now this is my table. This is my table. If you have this magnitude at the origin and this slope table, then you can comfortably draw the resultant magnitude plot. So what is the resultant magnitude plot? Again, take this as omega, say it as 0.1, this as 1, this as 10, this as 100. So let us take the magnitude as 0 dB here, this as 20 dB, and this may be 40 dB, this is minus 20, something like that. Okay. Maybe you can take this as 0 dB. So let me slightly alter this, let me slightly go. because the slope is always coming down, so let me have some space at the bottom. Let us consider this as 0. Let me consider it as 20 dB. This is minus 20, this is minus 40. So now at what is magnitude at the origin? It is 20 dB. So this is omega is equal to 0.1 radian per second. This is the magnitude at the origin. Now where is the slope starting? Does the slope starts at 10 radian per second? So whatever magnitude at the origin is there will continue till the first cutoff frequency. Where is the first cutoff frequency? It's at 10. So it is this point. So this will continue till there. No slope. Magnitude is 20 dB per decade till the first cutoff frequency. After first cutoff frequency, what is the resultant slope? Minus 20. So come down by 20 dB, go by 1 decade, draw the line. So till first cutoff frequency, retain the magnitude at the origin as the magnitude. So now slope will start changing from 10 radian per second. So at 10 radian per second, what is the resultant slope? Minus 20. So come down by 20 dB, go by 1 decade, you will get the slope reference, put it as, now this is minus 20 dB per decade is the slope. Then so next cutoff frequency is at 100. So you are there at 100 now. At 100, what is the resultant slope? It is minus 40. So come down by 40 dB, go by 1 decade. Now we can see the slope changes. Slope changes, and this goes till the end because there are no more slope changes over here. So now this is the slope of minus 40 dB per decade. So this is the overall resultant plot. So suppose if this was continued as minus 20 per decade, it would have went like this. Now since there is a change, it actually taking a change in slope at 100 radian per second. You can see this is 100 radian per second. I am just approximately writing. This is 10. This is 10. So is this not the same how we got this one? So is it not 20 dB, then minus 20, then again minus 40 dB per decade? So here we draw this by drawing this, and then finally we add it. So this can be totally eliminated if you have this magnitude at the origin and these slope table, which will give you the magnitude and the slopes at what frequency, what is the slope and what is the resultant slope, so that every individual or term slopes and cutoff frequencies are captured in the slope table, so that it becomes easy for drawing the magnitude plot. Whereas the phase plot is the same. The phase plot, there is no of course there is no requirement of shortcut. So you have the phase equation, you substitute the values of omega for different values omega, what is the phase, you just plot it on the graph sheet on the So this is the simplest way of plotting the magnitude plot of a system. This is, we call it as Bode plot. Thank you. So we will see in the next video how do we plot the graphs with a pole at the origin and how do we plot it on the semi-log sheets.